Yeah, so so the project is for this like SpaceX manned mission in like
Mm-hmm.
2025, right? So it's like it's been a while since we've actually had a manned mission to the moon. I think like the last time they did was like in 1971,
Mm-hmm.
1975-ish, I think. I don't know. So the project is like I'm working more on the communication end of things where it's like you kind of want to send out signals from like the Earth to moon, right? And like you want to like have it back. And like I think like I mean the reasons are obvious for why proper communication is important. And over the past
Mm-hmm.
like 40, 50 years, we've gone so far in communication. So that's not it's kind of like a solved problem, or like we're kind of satisfied with like the performance we have with communication, except at special points in the moon, right? It's like so you
Mm-hmm.
have like the lunar south pole, which is like what we're most interested in. It's like geographically or like it's like spatially located in such a way that it's just hard for signals on Earth to directly come back without facing like attenuation or without facing, sort of like, just a lot of loss of signals simply because
Mm-hmm.
of how much it has to curve or how much obstruction is there between Earth and like that specific point of the lunar solar pole. The way you can get about this though is by using sort of like multi-path radar, where it's like you have like satellites around the moon, you have like space objects around like the Earth,
Mm-hmm.
like satellites around the Earth, like space objects around the
Mm-hmm.
moon. Instead of sending like a signal directly from Earth to the moon, what you do is like you relay it back from Earth to the satellite. You send it from the satellite to maybe another satellite, and then once the satellite gets a good angle of the moon, like you send it
Mm-hmm.
back to like that one. Now the problem with it is that like this is kind of like a more crudish method where it's like a lot of brute
Mm-hmm.
force engineering to sort of like time all the things right and like sort of ensure like the latency is kind of good. Um, my project is more so about like having signals. So like it's like a lot of it's more on the signal processing end. It's more about like
Mm-hmm.
designing signals that will sort of like allow you to get like sort of like good feedback or like good receiving power um, without a lot of loss or attenuation. So that's what I'm doing over the summer.
That's so cool. And it's actually really relevant because, making sure that people are receiving the content we want to send without any loss of viewership is something that we're very concerned about.
Oh yeah, for
Uh,
sure.
for example, good after morning and welcome to On the Dome, a podcast about how non expert college age youth think. And today, we're not just talking about communication, but we are also potentially talking about computation, which is something we're both interested in. But first, who are you?
Hi, I'm Gaurav. I'm Gaurav. I'm a sophomore at MIT. I'm majoring in 6-2, which is electrical engineering and computer science. I've lived most of my life in India, but my
Mm-hmm.
current hometown is Chicago. And yeah,
Sick.
from
Both
the
very
Midwest.
good places.
Yeah.
Um, so yeah, you are also an EECS major, like me. And one of the things that both of us are very interested in is just computers and machines and like what makes a computer? What is a computer? What is a computer?
I think at the end of the day, like from a very simple, like I think there's several levels of abstraction to a
Mm-hmm.
computer, right? There's like, you go, I think at the end of the day, though, I feel like it's just like a bunch of like electrons and wires with the electrons flowing at the right places and right times,
Mm-hmm.
really. And like that's just like the most basic abstraction you
Mm-hmm.
can start from, and then you go like deeper, like or like to a more higher level, and you get like sort of like an entire computer which you can interact with and do sort of things.
Totally. One of the things that I'm very, very interested in is like the concept of a Turing machine.
Yeah.
And for those who don't know, Alan Turing, we love him, great guy, saved us from Nazis. Um, he had this idea of the most simple machine that would be able to solve any problem. And then later, this guy named Bill Rappaport sort of summarized what Turing and some other early computer scientists and computer theorists he summarized what all of them came up with into the three great insights of computer science, which I will now tell you. Basically, the three great insights are the first one is you only need two states to represent any information. This is the idea of binary encoding. You just need a 0 and a 1, or an up and a down, or a electricity flowing and electricity not flowing. Then you only need 5 actions, which is to be able to read whatever is on your memory or your tape, to be able to shift the tape right and left, or shift the position of the memory right and left, to change whatever's in the memory to a 0, or to change whatever's in the memory to a 1, or whatever your two states are. So those are the 5 actions. And then 3 rules to combine them. So there's the sequence rule, which is first do this, then do that. The selection rule, if something's true, do this, otherwise do that. And then the repetition rule. While something is true, do this. When it stops being true, stop doing it. And I kind of blazed through those pretty fast, but they're pretty simple, like concepts and rules. And any machine that has the capacity to do those things can solve any like computational problem like that our laptops can solve or that the supercomputers can solve or anything, given that it has enough memory.
No, yeah, it is super fascinating with how like just like ones and zeros and like the five basic operations you talked about and like the three sort of like ways you can go about like your operations. You can do so much and like that's I think like it's really fascinating. And so when I talk about like the levels of abstraction and like that being like one of the more basic levels, but that really enabling every other sort of like level of abstraction, it's super fascinating if you think about it. You know, it's crazy.
And then there's also like the EE side of things. Are you more on the EE side of like circuits and all of that?
Yeah, for sure.
You want to talk a little bit about circuits and how that plays into things?
Yeah, no, for sure. So, the thing with like a 1-0 state, like there are like several reasons why we do a 1-0. There's also been like sort of like a ternary or like trinary computers or sort of like that. A lot of analog computing's coming into picture now, which is super exciting. I think it's kind of like making a comeback because I remember like a lot of
for
people.
our audience, like what's analog computing?
Yeah, for sure. So a lot of traditional computing, or like computing you've done so far has been like ones and zeros, right? It's been like sort of you store data in the form of like ones and zeros. You do a lot of things in the forms of ones and zeros, or you do everything in the forms of ones and zeros.
Yeah,
actually.
And there's just layers of translation to get it to our pretty laptop screens.
Exactly. Yeah. What happens with analog computing though is that now there's no ones or zeros, or there's no like discrete steps between like 0 and 1. It's more so that you have like a more continuous sort of idea of a signal, and you feed that into a computer, and the computer does again like it has a very more a more analog calculation or analog approach, and outputs again like an analog signal. So like now you're moving away from like the 0-1 domain to like a more like continuous domain.
So going from like discrete steps and states to like
a more continuous like flowy kind of states,
yes.
Right?
For our audio only listeners, we just did a wavy hand motion.
Oh, is it ASMR in a way?
It can be.
Oh,
we
that's
can
so cool.
do an ASMR podcast.
That is so cool.
We don't usually, but you know, we'll see where the conversation takes us.
I see. Nice. No, Alan Turing was a great guy. It's such a cool fact that because of his like work on like the Enigma machine and stuff, it's like historians have predicted that it's like that kind of single-handedly caused like the war to like be shortened by 2 years, saving like 900,000 lives, which is like it's so powerful. Yeah.
So for those who haven't watched the movie, first of all, go see the movie, The Imitation Game. I'm sure there's also a lot of great books about it, but basically Alan Turing had this idea for this machine that essentially is kind of like the machine I described. It would have 2 states, 5 simple actions, and then you could give the machine instructions on what actions to do when, and it could solve different problems. And one of the very significant first models he built of this was actually a code-breaking device to help break Nazi codes that were like encrypting their radio messages. And being able to break those codes allowed the Allies to predict, what ships were going to be attacked when, and be able to make strategic decisions to shorten the war and save so many lives. So thank you, Alan Turing, for that.
Yeah.
But also just his insights on like how and what a machine that can solve problems actually looks like is so interesting. And to me, what's always really interesting is comparing that to how our brains work. Because now we're kind of getting into like the age of AI and neural networks and like computing with perceptrons and all of that sort of stuff. So essentially, the simple summary of that is instead of computing how a tape machine would maybe compute, we're computing how a brain would compute.
Right.
And it's interesting seeing like what problems are more suited to that and what problems are more suited to Alan Turing's machine. Do you have any thoughts on like AI in general and how that plays into like what a computing machine is?
Yeah, I think so the way I think about it it's like with like a normal, I think like computers, so like the difference between like say AI and like normal like say like normally written code is that like the code just does a set of like instructions that like you kind of tell it to, right? And that's like pretty much almost what all code does. And AI does the exact same thing. Like it obviously will do what you tell it to, and that's like I think the beauty of computers is just that it allows you to like sort of like do tasks like repeatedly very quickly, and that's like it feels like trivial to say this, but I feel like that's just like it feels important to like emphasize just the fact that like it'll do whatever you try to and like very efficiently, very quickly in such a short duration of time. And AI goes more higher or like more deeper than like say like functional code in the sense that if you effectively ask it to learn something or it comes from you're effectively making code that could sort of like that kind of has a brain of its own, or in the sense that that has some sort of memory of its own, that if you ask your code or if you ask some piece of AI to see something, it'll probably remember it and memorize it, or like or you sort of like have it like learn different things based on what you give it. And it's fascinating to me how like I think human brains work the same way, right? Say like you want to ride a bike. The first day you kind of like you ride a bike, you kind of fall, you learn from your mistakes. And then the next day you go out, you're probably still a bit shaky, but you know the mistake that you made the day before, like you want to correct that mistake. And a lot of AI, say like especially like this one field of AI, say like reinforcement learning, right? It's super like I was reading this like paper where it's how kids like how like drawing similarities between like say like the model of reinforcement learning and how like kids learn, right? It's about like the idea of like, or like it's more so like it's an interesting thing. I could probably go for a tangent about like sort of like the relation between like say like computer science and something like psychology or something, right? But this was like a paper kind of like attempting to sort of like drawing the connection between the two. And what happens in reinforcement learning is that like if your AI or if your model is doing good, you do give it a reward, and if it's doing bad, you sort of punish it or you give it like a punishment or something, right? And
you turn it in the other direction.
you turn it in the other direction, right? And I think like a lot like I feel like as a kid I kind of learned the same way too, like I'd get like good scores in exams, or like do good stuff in school, and like I'd get praised, and like if I do bad stuff I'd get like disciplined, or like I'd get punished, right? And I feel like just like the fact that like you're nudging like it in the right spot, but at this like so just the moment that like you so a lot of the learning's happening by itself, so like you're even like as a child like you kind of learn by itself. It's just that like your environment's kind of pushing you to the right spot, and like I think that's a pretty interesting idea.
Yeah, definitely. I'm actually, that made me think of another comparison, which is between like circuits in the brain, and it can kind of, I think, illustrate for some people maybe the differences between regular programming and AI. So our computers are based on circuits, which are essentially wires that tell electricity to go in different directions. That's basically all a circuit is. And we can use different logic to say, okay, for this problem, we want to send electricity through at this certain point, and based on the path it'll tell us which output we're going to choose based on which like path it ends up following. And our brains kind of work in a similar way. It's also just electricity flowing from point to point, traveling different paths to solve different problems, just in our brains, also impacted by like things like neurochemistry and hormones. But the difference is, with a circuit board, it will solve the same problem the same way every time, and then if it has to solve a different problem, it'll solve the different problem the same way. But our brains can sort of, it's almost as if the electricity is like water, and it'll, as it keeps flowing through the same path, there's like sort of a rut built. And so it learns to solve that problem better. It becomes more familiar with the problem the more you solve it. And AI has a similar thing where the more it solves different problems, the more it remembers about what problems were solved and prioritizes, oh, I've solved this problem 10 times, I know how to solve it 10% better. Whereas a circuit board, it solves whatever problems it can solve equally the same way, the same every time.
Right, yeah, this seems to be like some sort of like, I think, invariant in a circuit board,
Yeah.
that like it's like there's this sort of restriction on the board to sort of like change itself by itself. And no, yeah, that makes sense why you have like sort of like algorithms, so like sort of algorithms that like sort of teach model, or like teach a computing sort of device to like sort of like how the brain does, like sort of like modify some numbers or some parameters here and there to like make sure that you get the right combination to solve the problem that you've seen before correctly, right?
Yeah, definitely.
Yeah. So based off of this, I feel like what my advisor at MIT works on, he works on neuromorphic neural networks, and the idea behind
Neuromorphic neural networks. Yes.
yes. so the idea behind that is you're more so emulating like the brain, but through a neural. You're thinking of the neural network as like you're not effectively making a brain per
Mhm.
se. It's like you have a neural network, and like there's like conventional ways we think about neural networks in terms of like weights and biases and like sort of like
Mhm.
numbers flowing through and being added up and being summed
Yeah.
up.
Basically, a neural network is the basis of how most AI works. It's involves a lot of math, and it's just math to sort of emulate a learning process
Right.
for our audience.
Yeah, so in a lot of conventional neural networks, like math is the basis
Mhm.
for like neural networks. It's more so how like in calculus you have, like sort of like finding like local minima, something like
Mhm.
that. So
So
that's
finding the
essentially
optimal solution
yeah,
to
finding
different
the
things.
optimal. So yeah, exactly. So like a lot of curve fitting in a
Yes.
sense, and that's how conventional AI has always like kind of like looked at it as like a thing you do with numbers, right?
Mhm.
I think in recent times to say like the work that my advisor does. So it's super cool. So what he does is like instead of like sort of doing operations in like the numbers domain, he does operations with light, right? So
Ooh.
he has like this neural network and like the weights. So weights and biases. Yeah. So like for those of you who don't know, like so
Yes.
weights or biases are like certain like numbers or like they're typically understood as numbers in like a
Mm-hmm.
conventional neural network, which um define a network's arc like or which sort of like make a network, right? There's kind of like
they
properties.
tell basically how important maybe different factors in the network are. So if you have a neural network to like identify cars from planes, maybe there's a lot of weight put on. If it's more colorful, it might be a car because maybe planes are only generally white in pictures, or cars are more colorful. So like color could be really heavily weighted as an important thing to look at, but maybe I don't know, having windows is not as heavily weighted because both of them have windows, so it's less
Yeah.
weighted in distinguishing the two.
No, yeah, exactly. That's essentially the idea, right? So like you have like weights and biases, and they kind of like define a network, or they're what forms a network, and they're what allows you to go from like say like an input to an output, really.
Yeah.
So like you give it a number, or like you say you give it like an image, right? And then you have like your weights and biases sort of act on it, like you multiply it by the weights, you add an offset of bias, and you get like an
Mhm.
output.
It's almost like the neural network's mathematical personality.
It is, yeah. No, it actually I've never thought of it that way, huh?
Yeah.
No, it
We
is.
all have weights and biases. We all look at a picture of an airplane and think different things. So,
Yeah, no, for sure. Yeah.
anyways, tell
So
us about your advisor.
though, yeah, so the work he's doing is instead of like sort of like operating in like the numbers domain where you have like numbers and they perfectly add up and they perfectly multiply, um, he wants to have like a more physical like domain, or like something that's closer to what we see in our brains, right? Because
Mhm.
the way you can think about it is like, or like the way he tells me to think about it is more so that like like our brain doesn't like there's obviously like you have like electricity flowing through your neurons in your brain, and like so a lot of like the addition or multiplication that goes on in your brain is like it's not like perfect, or like in any physical system like a lot of like the good thing about math is it allows you to like remain theoretical at like a very like high level,
Yeah,
while
it's
like
perfect, no loss of electricity, no loss
exactly
of speed, nothing.
nothing, right? And like so what happens is in our brains, like you have like this sort of computation happening, but it's happening more so in the physical domain. It's happening
and so
more
there's
so
different factors affecting it that make it less perfect.
exactly, right?
Mhm.
So you're still having like the same fundamental operations, like you can still add electricity, or you can still like sort of like multiply or like integrate electricity in a
And
sense.
measure it in numbers, but
Exactly.
it's less perfect.
It is less perfect, right? But the fact that you can still do computation like allows us to like sort of, I think that's why like conventional like AI has always been like, oh, like let's have this theoretical set of like computations and numbers. So yeah, back to the thing, like so where he has like the light, like sort of like doing computations with light. Super cool, super interesting. One super interesting result that he found was also like seen in neuroscience, like which like so like what happens, so when you use light, right? So like he, for weights, instead of multiplying or like instead of using like a number multiplication, he uses some sort of filter that like, so when you pass light through it, it either gets like brighter or it gets like dimmer depending on like the weight of the filter. A bias again to sort of offset like the brightness of like light and stuff. And
Yeah.
then you just like shine light, and you have like the several like layers like representing like the layers of a neural network. And you add it, like you allow it to feed forward, and like when you're like sort of changing the weights and biases, when you're correcting the network, you correct like the physical parameters instead of like just changing numbers here and there,
So
right?
instead of like a computer model of some computation that you want to do modeling a brain, you have an actual physical light, and it's different parts of your brain, or maybe different processes in like a brain or another calculating machine, are represented by different like films that the light actually has to physically pass through,
Right.
and then you can really literally see the result rather than just reading numbers.
No, exactly. Yeah,
Mhm.
yeah. And again, like there's this concept in like say like AI or like neural networks more so in specific,
Mhm.
like called back propagation, where it's like so how like I think machine learning in the context of neural networks work is like you sort of initialize like a model, right? You have like a model with like random like weights and biases. So this means that whatever if you don't give it any train, like if it's untrained, like you give an input and it like spits a random output, right? It may
Right.
not make any sense. It gets better only once you provide like sort of information to it, once you sort of
Right.
like train it, right? And how it happens is that sort of once you train it, it tells you like how much the loss is, right? It tells you like how off you are by, or how much you need to be punished, or like how like, or if you're you're good and
Mhm.
like you don't have to change anything,
Yeah.
right? So the more you need to be punished, like the more you want to change your network parameters, or
Mhm.
like the more you want to change the things that define your network in the first place,
Mhm.
which are like weights and biases. So it's again like a lot of like calculus where you want to like sort of like change your weights and nudge your weights and nudge your biases in
Mhm.
the sense that would give you like the sort of like most change and loss, right? And again, like in the conventional AI sense, they happen by like numbers, right? Just
Mhm.
like sort of like you change a number a little more
Mhm.
so to get like a lower
Better
loss.
result, yeah.
Exactly, a better result. In the physical sense, it's more like with like the light and stuff, it's more so that it's very interesting. It's like how again like the entire process is happening more physically than numerically.
Mhm.
So it's like you're sort of like change like the filter is kind of changed by itself. Like they have like this kind of property where it's like if you pass in some sort of like current through it, right? Like you sort of like that changes the property of the filter in itself.
So the filter almost learns itself physically, because the way that the light passes through it based on the material of the filter, it will then adjust to make the light whatever the desired outcome is.
Exactly, yeah. It nudges the light closer to
Mhm.
what it really has to be,
Mhm.
right? And the most interesting part is so what happens with light is like you get a lot of error, right? Like there's
Mhm.
nowhere close to like, conventional neural networks where like, a 1 plus 2 is like always a 3 and it's not like a 2.95 or 2.9 or something, right?
Yeah.
So what they found with light was that a lot of light was just being like diffracted around, right? Like a lot of light, they were losing a lot of light simply because like, light as a physical thing is just, light is I'm not sure of this. I feel like light would be harder to handle than electricity. I feel like electricity, at least, like, I think it's just more easier to sort of like have it like go
Like
through
past
like a distance.
wire or something.
Yeah, I'm not too sure though. I feel like, but anyways, in this like lab, like they found out that they were like losing a lot of light, right? So their first instinct was to like, oh, like let's try to fix this. Like we shouldn't be
Mhm.
losing this much light, and this might actually cause our neural network to do worse because we're losing light and like lights what's
the
enabling
power?
exactly
Almost?
like it's like what's enabling computation, and like theoretical computation is key, right? The most surprising result is theoretical like precise or accurate computations actually may not be key. So like what they found in like the neuroscience, like in the brain, it's like they found a very similar effect where like a lot of electricity like that like goes to like through your neurons, like some of it is actually being dispersed out. And what this does like is that it actually helps your brain learn better because now it's like it's not overfitting in the sense that like it's sort of like because like electricity is being dispersed out to like other neurons instead of going where it's supposed to go, it's allowing it to like sort of generalize it more in the sense that like if you see a different pattern that's slightly different, like the way like your brain's kind of wired would sort of like see similarities to the pattern you saw before, and
Mhm.
it'll not treat it as like an entirely new thing, right? And
Yeah, so a good analogy might be for our audience, going back to the whole like water example, if electricity is sort of like water flowing through our brain, we don't want the water stream to be too powerful, because then it'll carve a very like narrow, thin little path, and then maybe we have a result that's like slightly different. We want it to go somewhere else, but since the path is so narrow and tight, it'll only give that result. It'll overfit to whatever problem we train it on. So if it sees a problem of, oh, this is a red ball, right, and I want to identify that it's red, if it overfits to the problem and it's like it being red means that it is circular and red, then when it sees a red truck, then it might give the wrong result because it's looking for a red ball.
Yeah.
And so maybe like dispersing it or having like a wider flow of the light or the electricity, losing actually some of the perfection will give us a better model, which is very interesting.
It feels counterintuitive. It feels
Mhm.
almost like oh, like on if you're losing accuracy, like losing accuracy on purpose allows you to do better rather than worse.
Mhm.
Or when you talk about like in the long term or in like a
Mhm.
larger scale picture, which is interesting, and that's exactly what the lab came through, right? It's like so the light that was being dispersed, it was actually going through like other like other layers, or like it was going through like other like nodes in the same layer. And while they thought it was like a bad thing because it's not like theoretically correct, like or like what you'd see in like conventional computing, it's still sort of like allowing it to sort of like instead of having that like sort of very strong jet stream that like in your brain that sort of will overfit or like will think of one thing as only one thing.
Mhm.
It allows it to sort of like widen
Broaden
the
your
flow.
view a little bit.
Exactly, yeah.
Mhm.
Exactly, yeah. That's essentially what it is. It's just like you broaden your view a little bit,
Yeah.
and it's super fascinating how they found this thing in a very physical system, and like they're drawing comparison to the very physical system to something that you see in like neuroscience.
Yeah, and it's like we often think of computation and the ideal computation is this very theoretical thing, theoretical tape machines and all of that sort of thing. But it's so interesting comparing it, I think, to physical systems and especially to our physical computers
Yeah.
that we have in our brains. I want to back up a little bit. You just told us a lot of cool stuff. How did you get into this? Like, how did
Yeah.
you get here?
For sure. It's actually a funny story, right? I think it's like I've always loved video games, I think, since I was a kid, right? But I think I had like super strict parents. So like they would never give me like a gaming console or like sort of like gaming CDs, right? I would cry so much for I would actually cry a lot, I think, just to have like a Xbox or something like that, right? I would actually cry so much that like my neighbors would come like knock on my door and be like, oh, is your son doing okay? Like, are you sure? Like, he's fine, that's so yeah, I mean, I don't know. I think I really like, I sort of like enjoyed playing video games as a kid. And so my dad, being the software developer that he is, he was just like, instead of like, playing games all day, why don't you like try to make a game one day, right? And that kind of like blew my mind. I think it's because more so like I've always seen this game from a perspective that like it's something to be played, and I never knew you could make it, right? So like I think like when you're introduced to the perspective that like, oh, I could be the one making these games and I could like have them be played by other people. I think like that's what kind of like, blew my mind. I'm like, oh, I definitely have to like take a look into this. So I had like an entire like Roblox phase, I think, when I was in middle school.
Didn't we all?
Didn't we all? Roblox is so good. Oh my god, yeah. But I moved on to like sort of like like using like Unity and Blender and stuff like that, right? And like sort of, and that's sort of like I think going on from like I think Roblox sort of like introduced me to like like coding stuff and like just like stuff you can do with the computer. And I think like seeing like I think like after I made like this very simplistic game with like very bad variable names and like terrible code, right? I don't know, it gave me a sense of satisfaction to see like, oh, what was in my head, I could see it in front of me, right? And I think that's probably like one of the first experiences that made me realize, oh, I want to be an engineer because like whatever's in my head, I want to see it in front of me, right? It's something that makes me happy. But like imagine how like it makes me happy to even think about it. So like imagine actually seeing it in front of you and not only having to think about it, right? But not only that, but I also felt like if you can do if you can use computers to sort of like make games, right? It's like it makes like the computers these days, like with the graphic cards they have, it's like you can have like games that are like look super real. They look super like the physics engines are like so good. They're so fast and they're so crisp. It's like if you can use computers for like, and you can use them for like not only making games, you can use them for like anything, right? Like almost almost every industry today just like uses computers. And it's like this like it's a relatively new field. It's like 150 200 years old or something like that, but it just
At
has
the very most.
at the very most especially. And just the amount of potential, like, or the amount of like untapped potential that we can see with the computer, especially say with like a lot of like computing advancements happening today, like say it like in AI or something like that. Super promising. And I knew like this was a field that I could definitely see myself not more so from like a game design perspective, but more so from like, oh, I want to create things and see them in front of me.
Yeah,
And yeah.
totally. It's funny. I had a different but similar journey. I actually was not a gamer growing up fully. I mean, everyone loves some Minecraft, but I wasn't fully a gamer. A lot of people were telling me, oh, you're a debater. You should go into law. Oh, you do social justice. You should go into that. Then my parents were like, you should be a doctor. There's not a doctor in the family. And
I'm sure my parents have told me that too, I think.
My grandmother, when I was like a little kid, she would tell me, like, I would always be like, Nani, tell me a story while I was eating or whatever. I would press her bindi. It was the story button. And she would always be like, so once upon a time, there was a little girl who was a doctor. And she would just tell me stories.
I don't know
about
why.
A doctor.
Oh my God, yeah. No, my grandmom would say the same thing too. She would be like, oh, we haven't had a doctor in the family for years. What if I get sick? You got to take care of me. Yeah.
But I think I got really into computer science. I did APCS and I liked that.
Nice.
But I think that through debate, through social justice, I was sort of introduced to the idea of systems and how all of the progress in the world was being made through systems and systemic thinking rather than individual change. The most powerful stuff was systemic change. And I found that for most cases, the people who are implementing the systemic change is not so much politicians, not so much lawyers, but really it's engineers.
Yeah.
And especially with computer science, it's all about building systems. It's not about building one little piece of code, but building something that can connect with the greater, computer science architecture that holds up our entire society at this point. So I really liked that computer science kind of matched that sort of systemic thinking. And then the other thing was, I've always been a very creative person, and computer science was the closest way to be able to use language, which is the medium I like most, to create sort of physicality, and like not even just physicality, but like more complicated systems than just words. I could, essentially talk to the computer in a language, and I could do anything I wanted. Honestly, it felt a lot like magic. You cast a spell, and you have to get all the different elements right, but then it'll do something completely magical.
Super cool. No, it's interesting, especially more so it's because like I think words like creativity or like systemic change or like like debating, they aren't usually associated with a computer science major in like the more conventional or typical sense. So it's actually like it's super cool that like you're like into it, and it's like it's wow, yeah. No,
yeah. I mean, I really think that computer science is, first of all, very beautiful and very like artistic and elegant. Sometimes it's ugly. Sometimes it's duct tape, or the code equivalent of duct tape over like a
oh, just like fixing.
Yeah,
yeah.
Make it work. It doesn't have to be pretty. But I don't know. Computer science has always felt, in a weird way, very physical to me and very almost tactile and like really like I don't know, very creative, definitely. And I think that more people, if they are able to see it that way, I think there's going to be so many new cool perspectives coming into computer science.
Oh, 100%. Yeah, I think a diversity of perspectives is really what you need to like push any field forward, and computer science is definitely like one of them.
Definitely.
And no, yeah, the fact the when you mentioned about how a lot of like I think even in like topics related to not only like policy, right? Say like climate change or something, right? Like if you like really look at it, I feel like a lot of times people focus on like it's like a lot of change can only happen through like politics or like by sort of like through policy or something, and legislation and all of that. And while that's true, I mean that's obviously true, right? I'm sure like there's been like huge impacts of like legislation, especially like more so in the recent years, to like help combat climate change. I feel like a lot of effort is also coming in from like say scientists or like engineers who are trying to like sort of like develop more like energy friendly like sort of like resources.
And like the legislation can't do anything if there isn't the resources of science and technology to back it.
Exactly.
Like often legislation is like, we're going to fund this industry, or we're going to make it so that using, like clean energy is cheaper, or we're going to subsidize these different things. But then the people actually implementing the legislation in real life are scientists, engineers, even architects, designers, all of those people, that the more creative and technical people.
For sure, yeah. I mean, at the end of the day, like I feel like like obviously the role of like legislation is like super important, right? And but also it's like they can only like make promises, or like what enables them to like make promises
Mhm.
of like a better future is really at the end
Yeah.
of the day, you know.
The
Like
people who are going to keep those promises, which
Yeah.
are often the engineers and the creatives.
yeah, no, for sure.
I think that that's honestly one of the best parts of MIT is that it very much emphasizes the idea of the artistic engineer, and also the idea of like mind and hands, so like makers and great thinkers, but also great thinkers who can put their thinking into action.
I think so too. I feel like coming into MIT, right? I think I was more of like a mind person. I always thought I'd do something more on theoretical end, or more something more abstract than something more
Mhm.
physical, right? I think coming to MIT, I felt like I've had this sort of like growing sort of like mm, almost like movement towards more so of like the hand, or more so like away from like theory and more towards practice, right? I was speaking about this idea like a few days ago actually with my friend who's like, since high school he's always done like these like sort of like like hand engineering projects where it's like, he's been super physically involved with projects
Mhm.
like that. And he had the opposite experience. He said, "Oh, coming to MIT, I feel like, I've always been this like builder and tinkerer and like do stuff with my hands. I've started thinking more, and I've started like
Mhm.
sort of like thinking theoretically and then converting that into something like that's more physical, right? I feel like, and I think the reason why is more so it's because like MIT doesn't sort of like prefer one over the other. I feel like, at least for me personally, I feel, or what I've like learned speaking from my friends, I think it's more so that, oh, if you're like more of like a mind person, if you're a more theoretical person, MIT pushes you to be more sort of like practically oriented.
Hands-on.
And if you're more like on the hands-on side, MIT probably pushes you to be more like theoretical.
Totally. It's very much a marriage of mens et manus, mind and hands,
Yeah.
as our motto says. And I think that definitely comes out in like every part of MIT. It's even just in the culture. Like one of the things the whole reason I started this podcast is like, we need to capture these conversations that we're having at the dinner table.
I agree with the dinner conversations part. I feel like interesting ideas come out of MIT dinner conversations, except for the times when, you're frustrated about
No,
like,
dude,
you
that's
said.
so true.
Wait, I feel like, yeah, exactly. Like, I think 50% of every dinner conversations is just like you ranting about some pizza that you had like a few
Mhm.
days ago, or like that you have due like in 30 minutes and you're
Uh-huh.
still eating, It's, yeah.
I know. I have a pizza due in 30 minutes.
That is true. That is true. Oh my god, no, this.
No, but the other 50% is really interesting. You get into all
That's
the
true.
theoretical things I was talking about. You also just like have just really interesting. You learn so much about people. Like, you learn that, your friend has never eaten a strawberry, or you learn that like
That's weird.
it is weird.
How's that possible?
I know. It's very weird.
It's
But
like strawberry ice cream. It's everywhere. Like strawberry cake. It's Oh my god! Wow.
I know. So you like learn weird things about that, or like, oh, my friend happens to be a
Wait,
Regeneron scientist. Didn't know that.
I've never had a mango in my life. I'm kidding. I'm kidding.
I was about to
No,
be so
I'm kidding.
personally offended.
Mango's like my favorite fruit. Like
Okay,
I would,
good,
I would
good.
have to.
My
have
favorite
it.
fruit too, yeah.
Yeah.
I mean,
Oh, I
obviously.
love mangoes.
Oh my god. Well, now I want mangoes.
Yeah. Wait, it's almost summer. Yeah.
It's almost summer, and
Almost
then we
summer.
can get we usually get the Alfonso mangoes.
The Alfonso mango is
Yeah, yeah,
so good.
Yeah.
So good.
But like, and this can also be very apt dinner conversation is, what is the objective best fruit? And then people will just state their case. In my friend group, we do a lot of tier lists too of like, what is the best
Oh,
color?
that's where I see the Simmons thing. Oh,
Yeah,
that's you
yeah.
guys. That's you guys. I
Mhm.
see. I see.
Like, what is the best color? What is the best state? That one is very controversial. What is the best, like.
What do
all
you
the-
think the best state is?
I think the best state is Washington State. Of course, I think the best state is Washington State.
Okay,
Um,
I asked the wrong person. It's crazy.
But no, the best state is objectively Washington State. But all
Mm.
states are great. We love, very fun. That's one of the most chaotic, but one of the most interesting things about the U.S. is definitely the system of states that we have them. But yeah, all sorts of things. Like, and I feel like we get really, really into all these conversations, and that very much exemplifies the mind aspect of MIT. Very deep thinkers, if very weird thinkers.
Yeah.
And then obviously there's the hands part with all the maker spaces and even the art around campus. There's so much art
Oh, there is
everywhere.
actually, yeah.
Mhm.
And like those art galleries that they haven't showed, like like the student center or something.
Mhm.
Very
Yeah,
cool.
definitely. Would you say so? One thing about you is that you were not here last year.
I was not here last year. That
Where
is
were
true.
you?
At this very time,
At
or
this very time, at this exact
wait,
time and moment
on
last
this
year.
exact date time, I was quarantining for COVID. Actually, it's the funniest story. Oh my god. So I was at Purdue actually
Yes.
last year. So I think I got COVID. I don't even know from who. I was just super sick one day,
Mhm.
and I'm like, oh, do I get tested? So I get tested, and it's COVID, and I'm like, oh my god, this is like the first time I'm having COVID,
Mhm.
right? Like, it was weird. Having COVID was weird. It was also fun in the sense that like I only had symptoms for a day, and that's when I was kind of like not isolated. But when they did isolate me, they sent me to this another like hotel kind of thing,
Mhm.
where like I was just like chilling by myself. And like initially, I think it's also like an interesting kind of concept where it's like, at first I thought it'd be good because I'd have like more like me time and stuff like that. You know, it's like 7 to 10 days. You know, it's like you're all by yourself. You can do like whatever you want, and you have like PSET extensions and like all that, right? And I'm like, oh, I'm gonna have like the time of my life. I think I did have the time of my life until like day 2 or day 3 when like I'm the only person there, and I'm like, oh, it's like I feel like it's
crazy.
exactly. I feel like you have to be surrounded with people to like not go
Mhm.
crazy after a point. I think.
You know what's funny is that here, if you get COVID, instead of sending you
Your roommate goes.
your roommate gets
I don't
banished.
understand it. I don't understand why. Why does that matter?
Well, it's fun because pretty much probably at this exact time last year, one of my friend's roommates had gotten COVID,
Oh.
and so my friend was sent to Tang Hall to one of the graduate dorms here
Yeah.
and had a big suite, and so we were like, okay, sleepover, and
Yeah.
so we spent like a whole weekend basically living out of Tang
That is
Hall.
so fun.
Us and like him and like 3 of us like as friends, and we were just like we had sleepovers, we all hung out, we like put like we like brought our like mattress pads and like put them all on his floor
Nice.
because he had like a really nice big room, and so that was fun because he didn't have COVID, and so we could all hang out with him, and then the roommate got to at least like stay in their nice room
That
and,
works out
like,
pretty well,
was
no? Yeah.
sort of familiar, like in the familiar space, but it's definitely not the norm to do that because then obviously the sick person is very much still in the building.
Right. No, for sure, for sure.
Mhm.
What do they do for like the COVID person? How do they what happens for food and stuff?
So they'll have usually someone deliver like meals.
Yeah.
Or they also you get like $100 Grubhub
Oh, I've heard of
credit
it,
too,
yeah.
so you can like DoorDash stuff. Well, I guess Grubhub stuff. Unnamed food delivery corporation, you can do that.
Mhm. Nice.
We have no sponsors as of yet. Want to keep my options open.
Oh yeah, that'd be exciting, huh?
Yeah, that would be exciting. I would love to be sponsored by insert unnamed food corporation. But no, it's very interesting how different colleges do it. But you were at Purdue last year,
Yeah.
so was that a very different experience than it is at MIT?
I mean, like yes, because it's a different college, it's a different state, it's different people, it's different vibes, different. I mean, like I would argue though fundamentally it's the same thing, right? Like
Mhm.
fundamentally, like like colleges work the same way. You have classes, you have PSETs, you have friends, you have like
Mhm.
stuff you do outside of classes and stuff like that. But at the same time, there's like subtle differences here and there that make a college like unique
Mhm.
in a sense, and like that's to each their own college. I feel like.
Definitely. And I feel like, I mean, I've definitely been thinking about, we just had Pi Day, so we just got our new batch of admits. We're going to have pre-Frosh weekend, which we called Campus Preview Weekend, is coming up. So we've definitely been thinking a lot about this. And I think really everyone ends up where they need to be.
Yeah.
Yeah. It's very cool. It's a good system. And, speaking of, we've just spent a lot of time talking about
Systems and
very good systems. Do you have any closing thoughts? You have anything you want to say while you're still on the air?
while I'm still on the air. Not really. I think a lot of like if you're listening to this, if you've gotten so far, right? I'm sure you must be like a very curious person or very, like you must have been listening to a lot of this. I think at MIT, what I've heard is to like, just do your best, right? I think like at the end of the day, it's like I think this is also like one value that I've like heard from my family and like just it's a strong value. It's just, you can be like bad, or like you can be miserable after like, you know, a few years, and you can like work your hardest and still like things may not work your way, right? But at the end of the day, you know, it's like if you've sort of, you know, like if you know you've tried your best, or like if you know you've put your best foot forward, right? And like then you have that satisfaction that, oh, at least I did whatever I could, even if it was not enough, I did whatever I could, and
Yeah.
I've come here. And I feel like, yeah,
Yeah, definitely. And I mean, at the end of the day, even if we go in completely the wrong direction, it's just more information for our own neural networks to
True.
correct and get better.
backtrack, yeah,
Always getting better.
always
so-
getting better.
On that note, thank you so much for listening, and this has been On the Dome.
Cue closing music.
Cue closing music. Actually, we do have originally.
You actually have one?